4 different outcomes, we're going to do the same thing with predation. You're going to have 4 sheets with 4 different outcomes. But whereas competition you needed 2 graphs on each sheet, with predation you're just going to have 1 graph on each sheet. Okay? So for the entire assignment 3, you'll have 12 graphs. You'll have 8 graphs for competition, 2 on each of the 4 sheets, and then you'll have 4 more graphs for predation, 1 on each of the remaining sheets. So the 4 kinds of competition outcomes we can have is 1, the least interesting, and this is where you just have a really wimpy predator. The predator isn't good enough at killing prey and turning it into new predators, and basically what happens is the prey, or the predator rather, will go extinct, and once the predator goes extinct, the prey will go to carrying capacity. Okay, that's your first outcome. Your second outcome is the opposite of this, where you have a predator who's way too good at what he does. Okay? And what happens when you have a predator who's too good and too efficient is that first you'll get a spike. So if this is the predator, he'll spike. When the predator spikes, the prey goes extinct. So if this is the prey will just go extinct. And then once the prey is extinct, the predator also goes extinct. Okay? So basically the predator eats up all his food, has nothing left to eat, and then dies out himself. Okay, so this is either called self-annihilation, or you can call it mutually assured destruction, whatever you prefer, but both species die. Okay. The third possibility is similar to what we did in that very first assignment 1, where we have limit cycles. So what you're going to see is you have a prey species that's growing. As the prey species is growing, you also have a predator that's growing. But then the predator starts to catch up with the prey, so then the prey crashes. When the prey crashes, then the predator crashes. And then as the predator is crashing, then the prey rebounds. Okay, so you get these cycles. And basically the predator is just chasing the prey through these limit cycles over time. Okay, and so you'll just see them bouncing between the same peaks over and over. This will be your third outcome, limit cycles, where both the predator and the prey are bouncing between 2 extremes, or 2 values, oscillating between 2 values and repeating the same ones over and over. Well, the fourth one, and this is the one that's going to be most challenging to produce, is damped oscillations. So what happens is it looks like it's going to do a limit cycle thing, but then it kind of gets itself under control. So the prey is going to jump, do a little wave, and then it will kind of taper off and equilibrate at a constant value. Whereas a predator will just kind of come up and just track and stay. They'll both end up at an equilibrium value. Okay? So this is what you're looking for. You're looking for some initial oscillations, but then they flatten out and you end up at just a straight line. Okay, these are the 4 different outcomes you need to have. So I'm going to show you how to code these. The nice thing is that we're telling you the values of almost all the parameters to use. So the encounter rate, that A, handling time, the H, your conversion efficiency, B, all those we're dictating for you on each of these runs, as well as the growth rate, the intrinsic growth rate of the prey. What you need to play around with is the death rate of the predator. Okay? I'll tell you it's going to be a value between 0 and 1. Okay, but it's going to be a very narrow range at which you can get all 4 of these possibilities. So you're going to have to do a bit of trial and error. So, open up a page. We'll do just like we always do with time, prey, predator. You're probably going to need a lot of time steps for this. I'm just going to go ahead and do about 800 of them. So now these equations are a little bit more complicated. For your initial prey and predator population abundances, I like to choose 50 and 5. You don't have to choose 50 and 5, but you're going to have to choose a predator level that's much smaller than your prey level. If you have too many predators, you're going to knock your prey down to 0 right off the bat. You won't get a good simulation. Okay, then we also need to have K, R, A, H, B, D. Okay, K, just choose a value between about 90 and 110. I'll just pick 99. Your R will be dictated. We'll just go for the first one where predators go extinct. This is 0.8. Counter probability is 0.1, 1.5, 0.05. And then to begin with, I'm just going to pick a death rate of 0.01. Alright. So for the prey, just like always, pick the previous population abundance times the exponent. Now you have to have your growth rate. Set that aside with dollar signs. Now we're just going to put in that logistic growth equation. Okay, so this is going to be just like what you did before. You're just going to have to put in that logistic growth. So, have your K minus N divided by K. Now you have to discount the effect of predation. Okay? So I have a subtraction sign. You're going to have A times P. So encounter probability times the number of predators. Divide that by 1 plus, that's your type 2 functional response, that Hawley's-Fiske equation. And then you just subtract the death rate. Okay. So I'll come back and highlight this so you can copy this down, but I want to go ahead and move to the predator. So similarly, start with the equal sign, initial prey, and the exponent. Now here you're going to have to get that whole big thing. So first in the numerator, the B times A times N. Should be it. So then just like before, you have to do these 2-column simulations simultaneously because they're constantly at each time step cross-referencing each other. So highlight both cells. Again, to do that, just click and hold in the middle of the cell, drag it over. Once they're both highlighted, bring it over to that bottom right-hand corner, get the black X, and then just drag it down. Scatter plot, not line plot. Okay. And so this is not quite, this is actually the predator self-annihilation example. Um, so you would have to play around with the death rate. That's the only thing you need to mess with. But this is an example of that self-annihilation, where basically the predator spikes, the prey is driven to extinction. Once the prey is extinct, then the predators go extinct also. So this is what self-annihilation will look like. So just to show you, I already have it prepared. Notice I have the graph covering up the D so you can't see what the answer is. So I'll just show you what these are all supposed to look like. Okay, so this is your wimpy predator. He can't do anything, he just goes extinct because he's not any good. And then the prey just goes to carrying capacity. Notice I have a whole huge run on here because I'm just doing a demo. If this were your graph that you were submitting in the assignment, you would want to take a much smaller cut and your time steps so that I can see what this part of the graph looks like, because I have such a huge scale and it happens very quickly. You can't really see much detail in here. So you would want to cut this down to maybe like just 150 time steps. Okay, so then again, self-annihilation. Okay. Again, you'd want to cut it down, but again, you have a spike in the predator, drives the prey extinct. Once the prey goes extinct, the predator goes extinct also. Finally, not finally, but limit cycles. Okay, so this is what limit cycles will look like. So the prey keeps jumping up and down. Once the prey grows high enough and the predators start to grow, then the prey crashes, followed by the predators crashing, and they just cycle against each other over time. So this is what limit cycles will look like. And you notice limit cycles that they just keep bouncing between the same points. It's a repeating thing. Okay, finally, and again, this is going to be your toughest one to figure out. This is what damped oscillations will look like. Okay, so you have a little bit of oscillation, a little bit of up and down, but then it just peters out. And the predators basically just track along the bottom. Okay, so you don't want to have it just go down and equilibrate. You want to have some oscillations here for it to be damped oscillations. So I'm going to let you work on this the rest of the time. Go ahead and ask me any questions you need to ask about competition or predation. I'll be in my office tomorrow from about 11 until 1. So if you want to come in and get extra help on this assignment or any of your other assignments you're working on right now, you're welcome to. I'll try to